right? So we have been, come on, thing. No, it's not mirror. Come on, technology. All right. So we've been kind of talking about uh, reaction mechanisms. And in the process of doing that, we've talked about nucleophiles and electrophiles. We've talked about polar and radical mechanisms. We've talked about bond making and bond breaking processes. We've also talked about, in the context of reaction mechanism, arrow pushing, right? And then double-headed arrows versus single-headed arrows, and moving 2 electrons at a time versus 1 electron at a time. So we've actually talked about quite a bit. So we're going to add another layer to this, these mechanisms, and start talking about whether or not the reactions are, let me not say that like that. We're going to add a thermodynamic component to this. All right, so I sent a video to you dealing with reaction mechanisms, and so I'm going to introduce that, a little bit of that information, and we're going to jump in and do some more problems, right? But we're going to add in the thermodynamic and the kinetic component of that, right? So if you have a reaction that's going from, let me just write it this way. Let's say you have AB plus CD, right? This is a type of substitution reaction where you end up with AD plus CB, all right, on the other side of the arrow. Move this back some. All right. So that reaction can be exothermic, or it can be what we call endothermic. You should remember this from, I think, CHEM part 2. Or part 1, actually. Right, where you learned about, use the whole page right there. Hold up, add another page. All right.
Dr. S, can you scroll back up just for a little bit?
Yeah, I am. I'm just trying to add a page in here. It doesn't look like it's working. So hold up. All right, where was I? Here. Okay. Can you see that now?
Yes.
All right. So we're saying, what I'm saying, the point I'm making is that that reaction can be exothermic or it can be endothermic, and there's a way to find that out without actually, in GChem, if you remember, you did probably an experiment in lab where you did calorimetry, where you measured the amount of heat that a reaction gave off, or the amount of heat that a reaction absorbed. Probably use like a little styrofoam cup or something like that to measure that. A little homemade calorimeter. But here, when we talk about something being exothermic or endothermic, we can figure that out based on uh, the bonds, the energy of the bonds that are being broken and the bonds that are being made. All right. So if we're looking for exothermic or endothermic with with respect to a particular reaction, then we can look at this equation where the enthalpy delta H, right? We set that equal to the free energy and then the temperature is here, and then entropy is here, right? But if we negate the entropic uh, contribution to the enthalpy, then delta H and delta G are roughly equivalent, right? So what do you remember from GChem about enthalpy or delta H as far as like the sign of it? Because delta H is going to give us uh, an idea about the um, extent of reaction. Right? What do
Can
you
you repeat
remember about
the
delta H?
question? The equation for it.
Okay. What about if it's negative?
It's exothermic.
Good. A negative delta H means that a reaction is exothermic, right? If delta H is negative, then it also indicates that delta G, or the Gibbs free energy, is also what? Negative, right? So it's exothermic and delta H is negative, delta G is negative. And then we can also think about the um, equilibrium constant, KEQ, right? We can say that KEQ, right? We can say that for KEQ, if delta H is negative, then there's very little reactants left, star materials left, because KEQ is products over reactants, the concentration of products over the concentration of the reactants. So KEQ is going to be greater than 0, right? So all that information we can derive from delta H, calculating delta H. We can derive the delta G, we can derive whether it's exothermic or endothermic, and we can derive the KEQ. And then we can also make some make some inferences about the rate, right? Because rate is based on the rate constant, lowercase k, times the concentration of the reactants, right? So we can make some inferences about that as well. We can say, let me add another page here. Come on, man. It's not doing what I'm telling it to do. There we go. All right. So as far as K is concerned, or the rate is concerned, we can say if the reaction is exothermic, then the rate is going to be I'm going to say it in layman terms. It's going to be fast. The reaction is going to be fast, right? If that's the case, then the activation energy is going to be low, right? That's what we mean when we talk about the rate. Let me zoom in right quick. Right? So for a reaction that's exothermic, if we figure out delta H, we can make an assumption about delta G. We can make an assumption about KQ. We can make an assumption about the activation energy as well as the rate. Right? All of that information we can glean from determining delta H. If delta H is positive, everything is reversed. I'm going to abbreviate positive as plus VE. All right, so don't panic about that. If it's positive, then KEQ changes, right, from greater than 0 to less than 0. Delta G is also positive. The activation energy goes up. So delta G, double dagger, is increased, right? The rate slows down, and we say that the reaction is endothermic. So if delta H is positive, then it's endothermic. Means that it absorbs energy instead of giving off energy. Exothermic reactions release energy, endothermic reactions absorb energy. All right, let me zoom out, make sure y'all have a chance to get this down and take questions. Any questions about delta H as it relates to a reaction or as it relates to any of the other either thermodynamic or kinetic components? So exothermic reactions are fast, and they also favor the products, right? And they also have a negative enthalpy, a negative delta H. Any questions? All right. So let's jump in and do an example, and let's see if we can take this and apply it. All right. So we're gonna look at this example right here. Right. Let me say up front about the delta H and delta G. Right. So for delta G, oh, let me just do delta H first. All right. So for delta H, you can calculate that by looking at the sum of the bonds broken, the energies of the bonds broken, and the sum of the energy of the bonds formed, right? For any given reaction, you always want to break weak bonds and make strong bonds. So your delta H is negative, right? That's the goal. You always want to end up releasing energy and not needing energy, right? So for delta H, we can calculate it. We can say that the sum of the bonds broken minus the sum of the bonds formed is delta H. All right. So now that we know that, we can calculate delta H for any given reaction as long as we know the bond strength of the bond that we broke or the bond strength of the bond that we made. All right. So let's look at the first example. So we're going to go walk this down. If we read the instructions, it says apply the arrows to reach the product, identify the nucleophile, identify the electrophile, and then tell what type of reaction it is: addition, substitution, elimination, rearrangement, and then calculate delta H, tell if it's exothermic or endothermic, and then tell if KEQ is greater than 1 or less than 1. All right. All right. So let me go back because that I misspoke up here where I said about KEQ. KEQ should be, instead of less than 0, which would be a negative number. You can't have a negative KEQ. It should be less than 1. So less than 1 or greater than 1. I apologize for that. So make sure if you're taking notes, make sure you fix that in your notes. So it's going to be greater than 1 or it's going to be less than 1, not 0. All right. So let's take this first example. We're going to put the arrows in. So first, let's identify the nucleophile and identify the electrophile. And then we'll talk about the arrows. So which one do you think is the nucleophile and why?
Is it the H3C on the left side?
The nitrogen compound?
Yeah.
Yeah. So this is my nucleophile, right? Keep in mind, nucleophiles are electron donors. So you can see that nitrogen, even though oxygen has 2 lone pairs around it, let me fix that. Right, the nitrogen is a negatively charged atom with two lone pairs of electrons. So your nucleophile is most likely it can be negative or it can be neutral. But a negative nucleophile is more reactive than a neutral nucleophile. So that's my nucleophile. By default, this becomes my electrophile. All right. Now, knowing that that's my electrophile, how do I know where the electrophile is going to react? What am I looking for? Right. So once I identify my electrophile, I look for a polarized bond. Right. That's what I'm looking for. I'm looking for a polarized bond as my electrophilic site, or the site where the reaction is going to take place. Right. So I have a huge dipole here between carbon and oxygen. Right. There's a dipole towards oxygen that makes oxygen partially negative, and then carbon partially positive. So that's what I'm looking for. So that carbon right here, that's called what? Anybody help me out. That's my electrophilic site. Mm-hmm. All right, that carbon is my electrophilic site. So that's where the reaction is going to take place. Right there. Right. So once I identify the nucleophile, I need to know where it's going to react. And the way I figure that out is to find a polarized bond within the nucleophile, within the electrophile, and the atom in that bond that's partially positive, that's going to be the atom where the nucleophile attacks. It's not going to attack anywhere else. right? Oxygen, both oxygens are already electron rich, so you're not attacking there. And then this carbon is not polarized, so you're not going to attack there either. All right. So now we can put the arrows in. So that's my electrophilic site. So the arrows are going to come from what? What's another word we use to determine or to identify a nucleophile? We call it something else.
Proton transfer?
No, it's not. It's not proton transfer. That's happening with the acid and the base. It's a source, right? It's a source of electrons, and the electrophile is a sink for electrons. Y'all remember that from the other day?
Yes, sir.
Yeah.
Yeah.
So when you're doing a mechanism, the electrons always flow from source to sink, not the other way around. So my arrow, I'm going to add, it's going to look like this, right? From this pair of come on, stupid thing. This pair of electrons to this carbon. And it's a double-headed arrow. It's not a single-headed arrow because I'm taking both electrons from nitrogen and giving them to that carbon to make a new covalent bond between carbon and nitrogen. And then I'm also going to break the pi bond and give those electrons to oxygen. Is that okay? We did some of this on Friday, am I right?
Yes, sir.
All right. I'm telling you, reps, practice. You got to do more reps so you can get in the swing of this because it doesn't change. It's just the substrates are going to change, but the arrows don't, right?
Dr. Russell,
Yes.
what does that say when it says or neutral? What did it say before
Negative. Negative.
that? Okay.
So it's a minus sign with a VE after it. I'm just trying to save some space. All right. So that's the mechanism. What type of reaction is that? And how do you distinguish what type of reaction it is? How do you distinguish that reaction from the other reaction types that we talked about?
Is it addition?
It is addition. How do you know that?
I don't know. Just looks like everything just got added together.
So that was in one of the videos, right? If you take 1 + 1 and you get 1,
Yeah.
yeah, that's addition. But another way to determine it is to look at that pi bond because you're adding something to a pi bond. So anytime you attack a pi bond with a nucleophile, it's going to result in addition. All right, is that okay so far? So I agree with that. It's addition. So we put the arrows in, we show the mechanism, and we determine what type of reaction it is. And we identified our nucleophile and our electrophile. I erased something up here. All right, nucleophile is just abbreviated NU with a pair of electrons over the U, and then electrophile is, you can identify it as E+, right? And this is an addition reaction. All right, now let's see if we can figure out what delta H is. And in order to do that, we need to figure out what bonds we broke and what bonds we made. So we're going to do a table or a list, if I can write. So what did we break? Based on the arrows, what bonds did we break?
Pi bond?
Okay, good. What type of pi bond? You're right. But it's a specific type, right? It's a CO pi bond. Is that right?
Yes.
All right. So we broke a CO pi bond. And then what do we make? Did we make this bond right here between carbon and nitrogen?
Yes.
Yeah. Right. Is it a single bond or is it sigma or pi?
Pi.
It's a pi. Huh? Is that a pi bond? That's not a pi bond, right? It's a sigma bond. It's a single bond. A pi bond would look like this, right? Where carbon will be double bonded to nitrogen. But we only made a single bond between them. So we made a CN sigma bond. Yes or no?
Yes.
Let me fix this too, because I don't want you to think that that extends all the way across like that. It's just this bond right here. Right? And then the bond we broke, I got it highlighted already. We broke this bond. It's one of the bonds between carbon and oxygen. We broke the pi bond. We're okay so far?
Yes.
All right. So now we need the bond strengths. And so I have a chart. I got to scroll down to it. I actually need to move it up. I'm going to move it up. Come on. Come on, iPad. Do right now. All right. So we got a bond strength chart right here. And I'll show you how to read this. So you read it across. So if I want to find the energy it takes to break or make a CN bond, I find C and then I find N. All right. And then I'm just going to go across to that number. So for a CN bond, it's either going to be 305 kilojoules per mole or 73 kilocalories per mole, right? I like kilojoules. I like working in kilojoules myself. But whatever you work in, both values have to be, all the values have to be the same, right? You can't work in one unit and then for one bond and then another unit for another bond. So the bottom number is in kilojoules per mole. And then the top number is in kilocalories per mole. All right. So let's take that, the 305. We're going to stick that in here. This is 305 kilojoules per mole. All right. We're okay with that? And then let's see what the CO pi bond, what the energy for that is. So there's some multiple bonds down here. And so to make a CO pi bond or break a CO pi bond, if you make it, it adds 741 kilojoules per mole of energy. If you break it, then you lose 741 kilojoules per mole of energy. All right, so we're gonna take that number 741. I'm gonna go back to our problem and put it right here. Kilojoules per mole. All right. So now we know the energies of the bonds. We've shown the mechanism. We know which bonds we broke, which bonds we made. Now it's just a matter of putting the numbers into this equation. All right. And I had up here, excuse me, I had up here the sum, because sometimes you might make or break more than one bond, right, at a time. So if you break two bonds, then you're going to sum up those energies. If you break three bonds, you'll sum up those energies. And by the same token, for making bonds. If you make more than one bond, you'll just take the sum of all the bonds that you make or all the bonds that you form. All right. So I just need to take that and stick it into this equation. So I broke the CO pi bond, which cost me 741 kilojoules per mole. And then by the same token, I made a CN sigma bond, which was 305 kilojoules per mole. So the difference between these two is plus, hold up, plus 436 kilojoules per mole. Are we following that?
Yes,
Yeah.
sir.
Plus 436. What does that mean in terms of whether the reaction is exothermic or endothermic? That's a big number, by the way. Very big number.
Wouldn't it be endothermic?
It will be endothermic. Very good. It's endothermic. Why? Because delta H is positive, right? And if delta H is positive, the reaction is endothermic. It's endothermic, right? What else? What else do we know? What about delta G? Is delta G positive or negative?
Positive.
It's positive, right? If delta H is positive, then delta G is positive. So we know it's endothermic. Is the free energy is positive. What about the activation energy? Delta G double dagger. Is it high or is it low?
High.
High,
It's high.
right? That means the rate for the reaction is slow, right? So that means the rate is slow. The activation energy is high. Delta H is positive, is endothermic. And then what can we say about KEQ? Greater than 1 or less than 1?
Less than 1.
It's less than 1. So once we calculate delta H, we can extrapolate from that all this other data without having to do any further calculations, right? But in order to calculate delta H, you need to know the strength of the bonds that you made and the strength of the bonds that you broke. That's why we'll have that chart.
I have a question.
Go ahead.
I'm sorry. So why is KEQ less than 1 again?
Because for a positive delta H or positive delta G, what that means is that you have more reactants left than products, right?
Oh.
So for KEQ, when you say the equation for KEQ is products over reactants, if that's a big number, then KEQ is going to be a small number, right? So it's be less than 1. Does that make sense?
Yes, thank you.
All right. So all that information we gathered just by one simple calculation of figuring out the delta H for the reaction. And then if we had to, since it's endothermic, we can actually develop an energy diagram, right? We can say what the energy diagram should look like. Why is the chart not showing? All right. Let me add another page right quick so we can talk about that energy diagram. All right. So where did that come from? All right. So with the energy diagram, that's another way to express like what's happening in the reaction, right? So what you'll have for any given energy diagram is two coordinates, the x and y. On the x is time, on the y, or sometimes you'll see it written as reaction progress. And then on the y is energy. All right. And so with that being said, and this is all qualitative, not quantitative. All right. Unless you actually have the activation energy calculated. So for this reaction that we just did, we said it was endothermic. So what that means is that the reaction curve will look like this, where this is the reactants, this is the products. Right? And at the very top of that curve, this is what we call the transition state. So every reaction is going to have, hold up. Trying to see why this other stuff is still showing up here. Technology is not my friend today. That's all right. I can write it over here. All right. So here at the very top, what we call our transition state. Any reaction is going to have a curve that's either going to look like this or it's going to be, so this will be for endothermic. All right. So the transition state is the highest energy point on the curve. Right. It's also where bonds are made and bonds are broken. Right. So in the transition state, you're going to have partially formed bonds and partially broken bonds. Right. The thing about a transition state, though, is that you can't isolate it. Right. That's a very key piece of information. Right. It can't be isolated. It's only a theoretical. Right. So it can't be isolated. It's theorized as what it's a proposed structure, right? And then it's also the highest energy point on the energy diagram, and it's the place where bonds are made and broken. All right, so all that's happening, and you can tell by the name, right? It's a state of transition. The reactants are becoming the products. All right. So this is what an endothermic curve would look like. And then by the same token, if we had an exothermic curve, it's going to be different. So this is the reactants, this is the products, and this is the transition state. And what I didn't point out on the other curve, I'll point it out here. This gap between reactants and transition state, that is your delta G double dagger or activation energy. right? That's your so that's the amount of energy that it will take to get from the reactants to the transition state. Right, so that gap between the reactants and the transition state, that's the activation energy. And then the gap between the reactants and the products, that's your Gibbs free energy, or delta G. Right, so you can actually calculate delta G by taking the difference in the energy of the products and the reactants. So you can calculate that. The activation energy, you can only calculate experimentally. Right, so you have to actually run a rate experiment to calculate activation energy. All right, anybody got any questions so far about exothermic, endothermic? I think all this stuff is in the video, so it's really just a review. Right, so your curves are going to look different. The exothermic is going to have a low activation energy, and then when you compare that to the endothermic curve here, you can see that's a big difference, right? Much higher activation energy for an endothermic reaction. All right, any questions?
So,
Okay,
so
go ahead.
the delta H, if that's positive, then the delta G is positive too.
Yes.
Okay.
So what that really means, if delta G is positive, it means that the products are higher in energy than the reactants. Because when you take the difference, you're going to get a positive number. Right. See, you see up here, if energy is increasing in this direction right here, you following? P is higher in energy than R. Is that right?
Right.
So when you subtract R from P using this equation down here, right, you're going to get a positive number. So if delta H is positive, which corresponds to an endothermic reaction, then that means that delta G is also going to be positive because the product's energy is going to be higher than the reactant energy.
Okay.
All right. And then by the same token, if delta G is, if the reaction is exothermic and delta H is negative, look at the products and reactants down here. So the products are lower in energy than the reactants. So when you subtract R from P, you're going to get a negative number. All right. Any other questions? That's a good question. No other questions. Okay. It's either clicking or y'all sleep. One out the two. Let's do another.
No,
You said what? Say you sleep?
no, we're good.
All right.
Okay.
I'm just making sure. All right. So let's take this reaction. I gotta cut it because I don't want to erase that because I know somebody's gonna want to look at that later. I think. And let's see if we can cut that. I'll just paste that on another page. Tell you what, this virtual stuff is the real deal. 'Cause I promise you, if I was on the whiteboard, I wouldn't be doing all this cutting and pasting. But it's okay. It's life. All right. So here's another reaction. Let's go through same thing. Let's just break this down and look at where the arrows are, put the arrows in, determine what type of reaction it is, and then go through the thermodynamic content. All right. So which one of these do you think is your nucleophile? And I put lone pairs in on purpose because it's not just the lone pairs that determine whether something is a nucleophile, but it's where they are.
Wouldn't it be the carbon and nitrogen on
Yeah,
the
cyanide. That's exactly right. So this is my nucleophile. By default, once I identify the nucleophile, this becomes the electrophile, right? So now the question is, where will the nucleophile attack? How do you determine that?
Polarization. You gotta see.
Look for the polarization, right? So here, this is polarized this way. Is that right?
Correct.
Yeah. So the carbon is partially positive, the bromine is partially negative. So that means the nucleophile is looking at that carbon as the attack site. All right. So let's put the arrows in here. That's ugly. Sorry. Boom. And then what else has to happen? Look at the products. Did I leave off? I left off the bromine. I'm gonna write it in.
Don't you have to break that bond to bromine?
Yes. Why do you have to break it? You're right. I'm not questioning your answer. I'm asking why. It's a very simple answer too. All the way back to the first week of school.
So the carbon could be neutral?
Well, not necessarily neutral, but it's got to obey the octet rule, right?
Yeah.
If I don't break it, it's gonna have 5 bonds to it, right? So I have to break it. And notice how I'm doing this now. I want to be really clear about these arrows. The bond is breaking, so I'm starting the arrow at the bond, not at carbon, not at bromine, and then I'm ending my arrow on bromine. It means that the electrons from the bond are being given to bromine. Is that clear? It's very important where your arrows start and stop. All right. So then over here, you can see that now the bromine has been replaced by this cyanide group. What type of reaction is that?
Is it substitution?
It is. This is substitution. What's the leaving group?
The bromine.
Bromine. Good. All right. It's a substitution reaction. Now let's go through the thermodynamic and kinetic stuff. All right. Which bonds got broken? What did I break?
CBr.
Good. I broke a carbon bromine bond. And what did I make?
Didn't you make a carbon bond?
I did. Right here. I made a carbon bond here. And I broke a carbon bromine bond here. Good. Let's go back to our chart. Let's see what we got. So carbon. So here's carbon. And then I made a carbon bond. Right. So I go down here. Let me erase this. I'm going down to here. Right. So here's carbon. And then here's carbon on this side. So that's what I'm looking for. I'll read it across from left to right. So I made a carbon bond, and that says 347 kilojoules per mole. And then I broke a carbon bromine bond. Is that right?
Yes.
So then that's 285 because here's carbon and then here's bromine. So it's 285 kilojoules per mole, right? So bonds broken, 285. And then 347. Is that right?
Yes.
So what is that? 62?
It's
285 minus 347. 62 kilojoules per mole. And is what? Negative. Is that right?
yes.
Okay. What can you tell me now about that? Now this is delta H. Keep that in mind.
It's exothermic.
Exothermic. Very good. It's exothermic. And then it's a whole lot of other information that goes along with that, right? Once I
Yeah.
figure out it's exothermic,
H is negative.
I can do delta G,
Mhm.
KQ, and the activation energy, not numerically, but qualitatively. Is that right?
Mhm.
So delta G is also going to be what? Negative.
Yes.
KQ is going to be
Low. Less.
greater than 1.
Oh, greater. Yeah. My
Mhm.
bad.
So that's greater than 1. And then the activation energy is going to be low. Is that right?
Low. Yes.
All those things we can extrapolate just from knowing that it's exothermic. Right? If delta G, if the activation energy is low, that means that it's a really fast, it's a rapid reaction. Right? What would the curve look like if it's exothermic? What would the curve look like?
So wouldn't the reactants be lower in the exothermic graph?
Lower as in further down toward the x-axis?
Yeah, like the energy when you talk about like the energy and stuff.
It'll be the product that's lower.
Mm.
Because this is the activation energy. Right here. That's the transition state. And that's the activation energy. So exothermic reactions have low activation energy. So that means the reactants are higher in energy than the products because you're giving off energy. So you're making more stable products than you start with, than the reactants that you started with. So that's why energy gets released. If the reactants were lower than the products, then it would be endothermic. Follow on that or no?
Yeah.
Okay. All right, cool. All right. So we got to stop. I didn't realize it was 12:02. But let me stop sharing, stop recording.